Good afternoon, everyone. My name is Colby Hurd, and my group members behind me are Ryan Paradis, Joey Curesky, Tanner Morrison, and Autumn Tidd. And for our CO200 or PET Capstone 2 project, we built and designed an anaerobic digester. And she blacked out. There it goes. So in this presentation, we're going to go over a handful of different ideas for our project, including team goals, group teamwork. We're going to go over our design of the anaerobic digester, as well as the methane gas collection system. We're going to go over how we characterize the feedstock, the safe. We're going to go over how the safety measures that we followed during this presentation, how we characterize the feedstock, as well as, like I said before, the design of the digester and the methane collection. We're going to go over the results and have a little bit of a discussion of those results and give our feedback on anyone that may do this experiment and in the future for Capstone. And go over some of our unanswered questions, as well as look at our methane production and why we believe we got a little bit of a low yield for what was expected from our characterization of the feedstock. So for our team goals, our first goal was to design and create an anaerobic digester that produced methane gas from manure. And we also designed and constructed a methane gas collect. I'm just going to put that. Design and construct a methane collection system. We also designed a way to measure that methane that was produced. It's not working. Hold it to your mouth. It'll work. It works. Okay. Designed a way to actually measure the methane gas that we were producing. So we used water displacement in order to do that. So the water displaced, we then changed into a volume for our methane gas. And we implemented a system for monitoring the safety. So you obviously can get problems with your pressure and your temperature, as well as maybe leaking methane gas. And we wanted to make sure while we were conducting this experiment that we were keeping everyone in this group as safe as possible at all times. For group teamwork, we met every Wednesday at 4 p.m. to have an in-person discussion about what we have done and what we need to do for our updates and reports. Towards the end of it, we obviously had a little bit more to do over time, so we tried meeting on Mondays as well as those Wednesdays at 4 p.m. and have another in-person discussion. We communicated in a group chat while we were not in person, just to kind of communicate anything that we were calculating or any questions that we had for our reports. We shared all of our files inside of Microsoft Teams, just so that we could all update and see what everyone else was changing and make sure we were all on the same page with all of our reports. And we also met with a handful of different professors and other people that helped give a helping hand with our project. And when we did so, we tried to make sure that at least 2 or 3 of us were in that meeting, just so we had a couple different minds to ask different questions and gather the information together. We always kept constant communication as to what our roles entailed for every week, and made sure that we were all on top of what we needed to do and offered any assistance that our peers needed. And we created, updated, and stayed on task with the schedule to make sure that as a whole we were accomplishing all of our goals for our project and made sure we did not fall behind. Next is going to be Ryan Paradis talking a little bit about how we characterize the feedstock, how we handled our safety, and talking about some of the outside resources that we used. Ryan?
So first I'm going to be talking about the outside resources that we used. And big thanks to Professor Sadie Ali Ferreira, because she helped out a lot with organizing our group. And in the beginning, we had a little bit of a struggle getting everybody on task, and we had a few meetings with her, and she helped us out get schedulized and everything. And And she also helped answer a lot of questions we had about the project and was always there just to help out. And then we also had help from Professor Brendan Sarnacki with the methane gas production. We were looking for a way to measure how much we produced or how much was in the room so it was at a safe level. And he helped us, kind of guided us to what to get, and that turned into like a wall plug gas meter, which I'll get into a little bit more in a minute. And we also had help from Professor John Swalek. He went through a lot of calculations with us and figured out that even at our maximum yield, the room wouldn't be explosive and everything was going to be safe and we would be okay. And then our last thank you goes out to Joel Huff, who provided the cow manure. Even on a negative 60-degree day, he was still there and willing to help out. And we also had research on numerous topics, and we cited those sources in our final report. So for safety, it started out with a gas meter because we needed to figure out if the room was going to be explosive, and if we couldn't be in there, we had to make sure it was safe for everybody. So Tanner went out and bought a gas meter that plugs into the wall and measures the amount in the room. And that was thanks to Brendan Sarnacki. And Tanner also pressurized the system to make sure there was no leaks and we wouldn't have any methane leaking out everywhere. And we also, like I said before, had a conversation with Professor John Swalek, who went over a lot of calculations with us and figuring out how much methane we could produce and how much methane it took to make the room unstable and possibly be explosive. And we calculated through that at 100% yield, the room wouldn't be explosive. So no matter what, we weren't going to explode, so that was good. And we also went over daily pressure and temperature readings just to make sure everything was staying at a consistent rate and we didn't have any big issues or anything. And the next is about characterizing the feedstock. And basically to do this, we had to take a sample of the cow manure, and we had 30 pounds in total, and we took a small sample, put it into a soup can, which we took the weight of, and then we put it over a fire for multiple hours and basically cooked all the water out of it. And through this, we got the dry weight of the feedstock, and we could figure out that there was 130 grams of moisture in our sample. And this led to us figuring out that the 75.3% water content in our manure. And through that, we went through another calculation and figured out that we have a possible yield of 375 liters of methane. And next up is Autumn Tidd, another member of our group, and she is going to be going over the design and results.
So going through the design process, we had a few different ideas on how to build it. And at first, we were thinking about 3D printing it and then segued away after the meeting with Swalek and Professor Ali Ferreira. And our parts list ended up including the 30-gallon drum, a 5-gallon drum, a globe valve, 4 to 5 feet of tubing, a tape measurer, temperature thermocouple, a space heater, a heat lamp, water, epoxy, 30 pounds of manure, and a vase. So building this, the first thing that we started with was drilling holes in the top of each drum, and then a hole on the bottom of the 5-gallon drum. And in the hole of the 30-gallon drum, there is a globe valve stuck into the hole with epoxy to seal it. And then on top of the 5-gallon drum, we did a T-fitting, and those are connected together with a barb fitting through the tubing. And then continuing on the other side of the T-fitting is connected to a 90-degree elbow that is epoxy sealed onto the bottom of the 5-gallon drum. So after this was completed, we pressurized it to ensure there are no leaks. And the reason why it is built like this, so that we have a closed loop system and we can collect the methane successfully. So the 5-gallon drum is filled with water, and when methane is produced through anaerobic digestion, it will displace the water and push it into the vase, allowing us to measure the amount of displacement. And then on the front, we have a manometer, allowing us to measure in pressure in inches per water. And the water allows us to keep back pressure so that we don't get any air leaking inside of the system. Next is results. We successfully designed and built an anaerobic digester and a gas collection system, and we ended up producing only 2.4 liters of methane, which is quite a small amount compared to what we could have. And we experienced 2 types of microorganisms during the digestion and created a baseline for other capstone groups and proposed questions for future teams. If a capstone group wanted to continue the research, we basically laid out the baseline. We got all the issues and kinks out, which is why we didn't produce that much methane, unfortunately. But next is Tanner.
Thank you, and I wanted to start the discussion about why our yields were so low. First, I want to talk about the data collection systems we did for the digester. We had 3 different types of measurements that was taken during the course of the test. The first was temperature readings of the biomass inside the digester. The second was pressure readings of the gas inside the digester. And the third is the volume displacement of the water. Obviously, the thermocouple measurement is extremely accurate, down to 1/10 of a degree, so that wasn't a source of error at all. And then the manometer was also extremely accurate within in inches of water, such a small pressure measurement, it's extremely accurate. The least accurate measurement we took was the volume displacement of the water, but even at a 1/16 of an inch of difference, it shouldn't have made much of a change in our scientific data. So this type of measurement system is obviously less reliable the smaller yield you get from the digester. It was more made for larger yields, such as liters and liters and liters of methane. So for our small yield of less than 3 liters, it's not extremely accurate, but it's good enough to get the point across. Next, I want to talk about some of the considerations why we got the low yield. The first is test duration. Obviously, you need a lot of time for these microorganisms to begin growing and everything. From our research, it can take up to 90 days for these microorganisms to grow, even in ideal conditions. Our total test was only 23 days total, so this was obviously not as much time, and this also doesn't account for the changes in test atmosphere. So our room was heated up and cooled down so we can try and keep the temperature more steady, which I'll talk about later. So this doesn't account for that, and then at the end of the day, we only had about 13 days of steady state inside the digester. So that was not ideal for the digester, obviously. We could have used even more time to let those microorganisms grow. The next thing I want to talk about is specifically the microorganisms themselves. There is 2 main types of microorganisms you aim for with a anaerobic digester. The first is mesophilic, and the second is thermophilic. Obviously, mesophilic thrives between 85 degrees and 100 degrees Fahrenheit, and thermophilic thrives between 125 and 140 degrees Fahrenheit. So we decided to go for mesophilic organisms because the amount of heat required to grow thermophilic organisms was just not feasible for us. It's dangerous to have 140 degree soup inside your house making methane. So we decided to go with mesophilic organisms, and it also made the heating requirements a lot easier for us to manage. The first thing we decided to do was use LED heating lamps, low wattage heating lamps. However, we found out very quickly that these were not going to put out enough heat to heat up the entire anaerobic digester. So we decided to move on to a space heater, and the space heater created its own problems. The biggest issue with the space heater is that it controlled the temperature of the room, so it cycled on and off automatically during the course of the digestion, and this caused kind of a cyclic temperature variation within the digester. So as it kicked on, it would heat up the biomass held within the digester, and as it turned off, that biomass would cool down, and this is not ideal for the microorganisms, especially when they're just trying to grow and there's such a small amount of them in the digester. For an example, commercial waste treatment plants, although sometimes using aerobic digestion, still a similar idea, and they want their plants to vary less than a degree every 24 hours. And in our test, we varied as much as 5 degrees every 24 hours. And I suspect it would be even more than that if we took our data more times over the course of 24 hours. So I think this was another large consideration, although not as large as the time that we'd had to digest. And lastly, I want to go over some unanswered questions we had. The first one is how to speed up the formation of the bacteria. Obviously, these are only hypotheses that we came up with after the fact. We did a bunch of research, but there's obviously going to be more ways that they could change our testing apparatus to make it more effective. The second is the most effective ratio of manure to water in the slurry mixture. This can be changed. It's a lot of anecdotal information online about this. A lot of places say to aim for about a 1-to-1 ratio of manure to water, and I think we eventually ended up with a little more water than manure than we were planning on. And then the last is aim for some more efficient micro digester designs. I know ours had no active mixing built into it just because of the complexity involved with doing that, but active mixing will shorten the amount of time it takes for those microorganisms to grow, and that could have been more a big thing with the design of the digester. If you had implemented some sort of mixing, it could have sped up the formation of those microorganisms and had better production of methane overall. I want to introduce Joey next. He's going to go over some conclusion and open up the floor for questions. Joey?
So in conclusion, for those who didn't hear in the beginning, our goal was to build an anaerobic digester and create methane gas from manure and collect the biogas with a gas collection system and as safely as possible. Our team met weekly, and we met in person. We also stayed in contact outside of class via group chat and shared files in Microsoft Teams. We had support from Professor Swalik, Professor Sarnacki, and Professor Ali Ferreira throughout the project for safety, design, and recommendations. To ensure safe operations, we conducted pressure testing to ensure that there is no leakage leaking methane into the atmosphere, or more likely Tanner's house. Daily pressure and temperature readings to ensure that nothing was out of ordinary, and a gas meter to measure any escaped gas to make sure there was none. We successfully produced 2.4 liters of methane. However, from the characterizing the feedstock, we knew that we can make 375 liters, so we weren't even close. Some of the unanswered questions we had were how to speed up the bacteria formation, the best ratio for the slurry mixture, which is the water and the manure mixed together, and more efficient designs for the small-scale digesters. We learned from the project that bacteria that forms inside the digester is very different from the bacteria that forms on the outside of the digester. And we also found, which we expected, that the effect of a small-scale digester is not nearly as much as a large-scale digester. And it takes much more assistance and help to get it started. So some recommendations for future students who wish to pursue this in Capstone would be to start the process as soon as possible, because it takes up to 3 months for the production of biogas. So the sooner you get it going, the more methane you can make at the end. And as Tanner discussed, monitor temperatures as closely as possible. The closer you are to 95 degrees, which is right in the middle, would be the best. Another one would be to increase the tank size for the digester, because the more microbial activity, the better the chance of bacteria to grow, which will make your methane yield more efficient. And the last one we had, which would be definitely the best recommendation, would be to contact an already in operation digester and see if you can collect microbial life from them to feed into the digester, which would help kickstart the methane production sooner. I'd like to thank everybody for their time today coming out to watch our presentation. And if anybody has any questions, feel free to ask.
With more time and a larger digester, could you improve efficiency?
Yeah, so if we increase the size, obviously there's a lot less that needs to go into it. You can let it set a lot easier, as well as our lack of like time after designing and constructing the digester. We didn't have enough time to actually produce the microorganisms inside of the manure slurry to actually digest the fuel and produce any of the methane gas. That's one of the big reasons why we weren't getting the numbers that we should have been getting.
Alrighty, thank you.
Good afternoon, guys. Great presentation. I had a quick question. With the large scale, do you think this might have an application in homesteading? Like, would other types of manure be applicable? Like, let's say chicken manure. Would there be an effective mix?
Yeah, I think that's one of the biggest things that this can be implemented in with off-grid homes and off-grid living. If you get once you wait the time for the anaerobic digester to start producing, you don't need to wait any more time when you add more stock into it. The microorganisms already established, and you can continue producing gas over and over and over again from that same microbiome. And any manure would work. Obviously, there's different yields for the different types of manure, but you can also use home table scraps and food just like that. Doesn't need to just be manure. Manure is just one of the most effective ways to kick off the production of a digester, and it's one of the most easy things to come by for most people using a digester.
Thank you.
Yeah, I'm not sure. We didn't do much research about human fecal matter, but the fats and the oils in it can be broken down a little bit more effectively by the anaerobic microorganisms than in a normal aerobic compost environment. They're a little bit better suited for that, especially with being able to live at higher temperatures and everything. It's definitely something that can be broken down more effectively by anaerobic bacteria.
So Professor Harmon asked a really good question about human waste, right? And one of the things we learned in Capstone 1 was about wastewater treatment facilities, and they do collect that methane from wastewater treatment facilities. Yep. I have a question. Of course they do, right?
Yes.
So, do you think that you could change your design to incorporate some sort of agitation system, and is that something that the next group maybe could do?
I think that we could, if you maybe use like egg beaters and you could seal that in with epoxy and use that so you don't have to open it up again, or have something like that will move it mechanically would be a good idea. I also think adding installation would help with the heating issue as well.
Did you have a chance to put together the lab, like a lab to use, like in thermo or chemistry?
Yeah, no, we didn't assemble a lab. We just kind of gave recommendations and then the baseline data of how to do it and what works and what doesn't.
So I also have a question about your yield and how it was 375 liters, but with the production of only 2.4. Basically, my question was, did you ever leak test or seal test any of your equipment to just see if you had any leaks and if you were losing any gas that way?
Yeah, so right after we built the digester, before we put any manure into it, start the process, we did do a pressure test to make sure there was no leakage. And then, what? Yeah, as well as the water to make sure that, make sure there's nothing leaks.
Thank you.
I have a couple questions. This thing's odd. Is the digester still in use now?
No, it was taken out of service about midweek last week, so I didn't have to keep monitoring it while we were writing the the final report and preparing for this presentation. I had it going for this the week before that as well, and we implemented that data into our presentation, but unfortunately, no, it's not going anymore.
And did you mix it at all during this process? Did you shake it up, or did you just let it do its thing the whole time?
No, I mostly just let it do its thing for the whole time. I know I didn't want to mess with the results too much by adding extra variables while we were waiting for it to produce. I know, especially if another group does this in the future, we don't want them to be starting off a couple steps behind if we did do something like that and didn't put it on the record. So I wanted to keep it as baseline as possible for the entire test.
I got a couple more. So how much cow sewage did you use? Like per day, I guess. Did you add every day, or was it like once a week?
So right at the beginning, we added the full 30 pounds,
Oh, wow.
and we mixed it up with water into a slurry. So that was the only time we ever did any mixing with it. Once it was in there, it was in, and we just let it process to give us a baseline.
Interesting. And then how did you measure the methane? Was it all just by calculations, or did you actually weigh it out some way?
So the water displacement system that we explained, it was, Ryan will bring it back up.
I might have dismissed it.
But that 5-gallon bucket on the right-hand side, that's where we collected the gas. So on the left-hand side is your anaerobic digester, and the gas would be lifted over into that bucket, and it would put pressure on the water, which then displaced the water into the vase on the plate in the front. And then through how much water was in that vase, that's how we measured it, measured how much methane we had produced up to that point.
Did you test it to see if it was actually methane, or did you just assume?
Well, seems how we have the actual, the tube going from the anaerobic digester over there. There's no way that slurry would be able to get up in it, over into the other bucket. It would have to be gas. Seems how it would lift up and go over through the tube.
Cool. Thank you. Anybody else?
Yeah, I think your last slide had recommendations for maybe the next group. The very last one was, basically get microbes that are already in production. So how did you actually get the process started? What did you use to get your process started?
So it was just done through heat and the manure that we collected from Huff Family Farms, and we put that in there because normally, like a big anaerobic digester setup, they use manure to kind of get the microorganisms going a little bit faster, as well as they put in food waste. That was just kind of, if we could use someone that's already gone through the time and hassle of getting the microorganisms up and living, maybe we could take some of those and put it in there and skip that process.
So you were relying on what was in the base material.
Yeah, the base material houses the correct microbiome to grow those organisms. It just takes time for them to begin growing and kick off effectively. So cow manure houses the correct stuff to begin the digestion process. It just takes time for that to get started. Any more questions, or?
In any kind of research that you guys might have done during the digestion process, did you look at what more commercial grade size digesters would get for a yield in terms of how much they could potentially make from their feedstock and how much they actually produce? Were you able to get like kind of a ratio, I guess, from like theoretical to actual?
Yeah, that's basically how the calculations we came up with were. We obviously didn't have enough yield to calculate that effectively. The yield numbers we came out were based upon other digesters, generally larger digesters that they base the yield on. They already have charts based on the amount of liters of methane produced per what type of feedstock you use. So that's what we based our calculations on, not off our actual project.
And another part of that is in the research, we found that they used 83% water in their manure. So ours turned out to be 75, so it also differs there. So even if we did it, the numbers wouldn't be relatable really, because it all depends on where your manure comes from. Any other questions? It was about a month old.
So do you feel like maybe some of the methane had already released from your feedstock? Like if you had brand new manure,
So we actually started digesting the manure before we put it into the digester, but it was a different type of organisms that use oxygen. And when it's in the actual digester, they're organisms that work under oxygen deficient environments. So we were already producing methane before we put it into the actual digester. So it's possible that we did lose some energy throughout that. Yeah, and the manure was frozen for quite a while, so we probably didn't lose much in the time that it was frozen. Any other questions? Thank you for listening.